Swayam Prabha. Digital India. Educated India.
Welcome back to the video course on fluid mechanics. In the last lecture we were discussing about the pipe network systems and unsteady flow through pipes or closed conduits. So, we have seen that as far as unsteady flow in closed conduits are concerned, say most of the time we have to deal with the water hammer or hydraulic transients when we deal with the water, or if it is oil then oil hammer, or it is steam, it is steam hammer. All this we have discussed in the last lecture. So, today we will discuss with respect to the hydraulic transients or water hammer, we will discuss the basic principles, we will discuss the governing equations and some of the method of solutions as far as this unsteady flow through pipes or closed conduits are concerned. Also, we will discuss say to reduce this water hammer effects, we may give surge tanks, especially in the case of hydropower projects when we connect turbines through a penstock, and then there is a the water first comes through the tunnel and then pass through a penstock, and then especially in the case of turbines when the turbine is switched off, turbine is not working, that means sudden shutdown takes place, then there is a very large water hammer or very high intensity water hammer may produce. So, in that case we produce surge tank. So, we may discuss today also the surge tank and its related theories. So, we will now come back to the unsteady flow in closed conduits or pipelines. So, as we discussed, so if you consider a simple system like this, here there is a reservoir and then it is say with the reservoir a pipe is connected or a conduit connected like this, and then to develop the theories with respect to such a system, a simplified system, say we assume here there is a valve, and then due to sudden shutdown of the valve, what happens with respect to the water hammer or hydraulic transients. So, you can see that whenever there is a sudden closure of this valve, there is a moving wavefront will be produced and it will be moving to the reservoir, and then again it may reflect back to the closed valve back, and then it will return back to the reservoir. So, like that oscillatory motions with respect to the water hammer will take place. So, with respect to this we will discuss now some of the theories and some of the governing equations with respect to this unsteady flow and hydraulic transients with respect to initially with respect to a single pipe system connected to a reservoir, and then with respect to the closure of the valve, a sudden closure of the valve, what happens. So, here say we assume that for the fully open valve the velocity V0 is velocity V0 at t is equal to time t is equal to t0, and then valve is suddenly closed. So, flow reduced to 0. So, here V is equal to V0 at t is equal to t0 time, and due to sudden closure the flow is reduced to 0, and then you can see that with respect to the movement of the fluid or with respect to the flow there is kinetic energy. So, due to the sudden closure this kinetic energy is actually transformed into elastic energy, and then what happens, the pressure rises and then pressure wave travels upstream. So, here due to sudden closure the pressure rises and then a pressure wave will be traveling to the upstream side, and then the wave again reflected from reservoir travels back and forth between valve and reservoir. So, here again it goes back and then it returns back, like that it will happen for some time until the intensity of the pressure reduces, or the hydraulic transient, the water hammer effects reduces, this wave travels will takes place, and finally the pressure stabilizes. And so, here you can see that there is a steady oscillatory flow, and once the valve is opened and closed periodically, say we can observe, say first the valve is opened and then closed. So, with respect to this valve opening and closing, we can see that periodically a steady oscillatory flow takes place. So, now we want to find out some relationships to connect with respect to the water hammer or the velocity of the wave front, and then how this can be connected with respect to the pressure which is building up with respect to the sudden valve closure. So, that is what we want to find out. So, let us consider the typical system which we have seen with respect to the figure here. So, we want to get the pressure changes caused by an instantaneous velocity change. So, we consider the same system. Here there is a reservoir and then a pipe is connected, and there is a valve which we suddenly close. So, here the initial pressure in the pipe, let it be P0 before the valve closure, and initial velocity be V0 before valve closure, and the initial density, let it be rho 0, the density of the fluid. So, now at time t is equal to 0, valve setting is changed instantaneously, and then you can see that due to sudden closure the velocity, pressure and density changes as we discussed in the previous slide. So, now say due to this sudden changes, let us assume that with respect to the valve closure. So, let the pressure change from P0, which is the initial pressure, to P0 plus delta P, and then similarly the velocity changes V0 to V0 plus delta V, and the density changes rho 0 to rho 0 plus delta rho, like in this slide. And then the pressure wave of magnitude, say delta P, travels upstream, so as we have seen, and now you can see that this wave which moving say to the upstream and then coming back like that. So, it has got a high velocity. So, let A be the velocity of propagation of pressure wave or water hammer wave. So, this pressure wave, it is called water hammer wave. So, this let the velocity of this water hammer wave be A. So, now what we do? So, here we can see that this is a transient system. So, if we superimpose this water hammer velocity A with respect to the earlier velocity V0, you can see that we can make this system into we can transform the transient system into steady state system by superposing this water hammer velocity. So, that we can write the velocity V0 is represented here as V0 plus A, and then V0 plus delta V plus A, that is after the valve closure changes. So, and the density is same rho 0 to rho 0 delta rho, and the pressure is P0 to P0 plus delta P. So, what we do here, it is a transient phenomena, that means the wave goes and comes back. So, it is a transient phenomena. So, that we transforms into a steady state phenomena by adding this water hammer velocity with respect to the velocity as in this slide. So, now here say if you consider the same system as we discussed. So, here now the velocity here is V0 plus A, and then here at the velocity changes. So, here the unsteady flow, as I mentioned, is converted to a steady state by superimposing the velocity A. So, here that is what we have done. So, now say we can find out what is the rate of change of momentum. So, here we can see that with respect to the change in velocity, there will be rate of change of momentum. So, the rate of change of momentum in x direction we can write as rho 0 into V0 plus A into the velocity change. So, the velocity change is V0 plus delta V plus A minus V0 plus A. So, this is in bracket. So, that is equal to rate of change of momentum with respect to this change in velocity will be rho 0 into V0 plus A into delta V. So, this gives this equation number 1 gives the rate of change of momentum in x direction. So, which is the direction we consider. So, here actually we consider the flow as one dimension transient. So, that is what we now transformed into a steady state by superposing this water hammer velocity A. So, the rate of change of momentum in x direction is obtained as rho 0 into V 0 plus A into delta V as in equation number 1. So, now if you neglect the friction, then resultant force acting on fluid in the control volume in the x direction. So, here if we consider a control volume, then the resultant force F acting on fluid in the control volume in the positive x direction will be F is equal to P 0 into A minus P 0 plus delta P into A. So, we consider the control volume between two sections, and then if the one section it is P 0 A and other section, that means with respect to the valve closure for the change in velocity we get P 0 plus delta P. So, the change in resultant force will be P 0 minus A minus P 0 plus delta P into A, that is equal to minus delta P into A as in equation number 2. So, now we can use Newton's law of motion. So, the net the resultant force is equal to rate of change of momentum as we have done here in this equation number 1. So, we can equate equation number 1 and 2. So, that from Newton's law of motion we get minus delta P into A is equal to rho 0 into A into V 0 plus A into delta V. So, net resultant force is equal to rate of change of momentum, or we will get this delta P, the change in pressure as delta P is equal to minus rho 0 into V 0 plus A into delta V as in equation number 3. So, we get the pressure change delta P by the equation number 3. So, here we can see that say through experiments or through various analysis we can show that this water hammer velocity is much higher compared to the normal velocity of fluid through the pipe or the closed conduit. So, this A, the value of A is to the order of about 1000 meter per second, but generally the value of V 0, which is the velocity of the fluid moving through the pipe, it may be to the range of 10 meter per second. So, we can see that here with respect to this delta P is equal to minus rho 0 into V 0 plus A into delta V. If we consider this V 0 is much smaller compared to the water hammer velocity, which is about 1000 meter per second. So, we can neglect this V 0 here, so that we can write delta P is equal to minus rho 0 into A into delta V. So, equation number 4. So, we have neglected this V 0 since A is much higher than compared to V 0. So, we get delta P is equal to minus rho 0 into A into delta V as in equation number 4. So, now we want to find out what will be the change in the pressure head, so that we can represent this P as rho into G into H. So, we can write this delta P can be written as rho G into delta H, which is equal to, as we have seen, that is equal to minus rho 0 into A into delta V. So, finally, we get this delta H is equal to this here you can see that here if we consider the change in density as negligible. So, we can cancel this rho 0 and rho. So, that we get delta H is equal to minus A into delta V by G as in equation number 5. So, if you consider water hammer or with respect to water movement, then you can see that this change in density will be much less. So, we can cancel rho with respect to rho 0. So, we get delta H is equal to minus A by G into delta V as in equation number 5. So, here please note that this negative sign on the right hand side indicates pressure increases for velocity reduction and vice versa. So, here the pressure increases when the velocity is reducing and then vice versa. So, this equation is derived for velocity changes occurring at the downstream end of the pipe and wave front moving upstream direction. So, similar way, if the case is reverse, that means here the case is if the the velocity change occurring in the upstream and then in the wavefront moving downstream, then this same expression sign changes, we can write delta H is equal to A by G into delta V as in equation number 6. So, here in this equation number 5 or 6, we get a relationship between the change in velocity and the water hammer velocity, and then with respect to the pressure change or the head change delta H. So, that is the significance of this relationship, since we get now a relationship between delta V, delta H and the water hammer velocity A. So, here G is the acceleration due to gravity as in equation number 6. So, now with respect to this figure here, this figure B. So, here say if you consider this figure B, we can see that the rate of mass inflow, we can see here rate of mass inflow to the system, the control volume which we consider rho 0 into A into V 0 plus A, since we consider now with respect to steady state system as in equation number 7, inflow is mass inflow is rho 0 into A into V 0 plus A, and rate of mass outflow from the control volume it is say with respect to change in density and velocity. So, it is rho 0 plus delta rho into A into V 0 plus delta V plus A as in equation number 8. So, now the increase in mass of control volume due to density change is small and may be neglected. So, that the rate of mass inflow is equal to rate of mass outflow. So, with this control volume, with the small control volume which we consider between section 1 and 2 in the pipe or the closed conduit, we can see that the rate of increase or decrease the mass will be much less. So, we can equate the rate of mass inflow to rate of mass outflow. So, that we can write rho 0 into A into V 0 plus A is equal to rho 0 plus delta rho into A into V 0 plus delta V plus A as in equation number 9. So, here we can simplify this equation to get delta V as delta V is equal to minus delta rho by rho 0 into V 0 plus delta V plus A as in equation number 10. So, here again we can see that even this V 0 plus delta V will be much smaller compared to the water hammer velocity A. So, that here in this relationship we can write delta V is equal to minus delta rho by rho 0 into A as in equation number 11. So, the reason is that water hammer velocity, it is the range of about 1000 meter per second. So, even the change in velocity of the fluid will be, which is flowing through the pipeline, will be much less to the range of 10 meter per second. So, that we can approximate delta V is equal to minus delta rho by rho 0 into A as in equation number 11. So, now let us introduce this with respect to the fluid movement. Let us introduce this bulk modulus of elasticity of the system. If you write the bulk modulus of elasticity, K is equal to minus delta P by delta rho by rho 0 as in equation number 12. So, we introduce K is equal to delta P by delta rho by rho 0. So, now with respect to this equation number 11 and 12, we can write the water hammer velocity A is equal to minus K into delta V by delta P as in equation number 13. So, here you can see that now this we got a relationship for the water hammer velocity with respect to the bulk modulus of elasticity K and the change in velocity delta V and change in pressure delta P. So, A is equal to minus K into delta V by delta P as in equation number 13. We have already seen here earlier this delta P is equal to minus rho 0 A into delta V. So, if we substitute back here, we get A is equal to K by A rho 0, or we get the water hammer velocity A is equal to square root of K by rho 0 as in equation number 15. So, water hammer velocity A is equal to square root of K by rho 0, where K is the bulk modulus of elasticity of the fluid considered and rho 0 is the density of the fluid. So, we finally what we get here, the water hammer velocity A is, we can see that it is a parameter which depends on the bulk modulus of velocity and the fluid density as in equation number 15. So, A is equal to square root of k by rho 0. So, the above expression gives the velocity of water hammer waves in a compressible fluid confined in a rigid pipe. So, if the pipe is rigid, we can use this relationship, but if it is pipe is not rigid, and then if it is elastic pipe, then we have to change this equation. So, so far the derivations we have considered the pipe to be rigid. So, A is equal to square root of k by rho 0 as in equation number 15. So, now say we have seen when the with respect to a sudden valve closure in the case of a pipe or closed conduit connected to a reservoir. So, the water hammer or hydraulic transient is generated. So, with respect to hydraulic transient, the velocity of water hammer, we have found a relationship, we have found the relationship with respect to delta H, delta here we have found a relationship with respect to delta H, the water hammer velocity and the change in velocity, and also we have found the relationship for the water hammer velocity as square root of k by rho 0 as in equation number 15. So, now we can see that as I mentioned, say in the case of a sudden valve closure, then a wave is generated, water hammer, the velocity is happening and a wave is generated and it is going back and again it is coming back. So, there will be a translatory movement with respect to the valve closed and the reservoir, and then periodically wave action takes place. So, now we want to, so with respect we have seen the what is the velocity of the water hammer, we have derived a relationship. So, with respect to this, now we want to analyze what is the governing, we want to derive the governing equations with respect to this hydraulic transients or the water hammer. So, now hydraulic transients, we have seen that depending upon the conduit in which transient conditions are occurring, we can have three types of systems. So, the transients, hydraulic transients in closed conduits, which we will be discussing here. So, like in pipes, and also the case of open channels also we can have transients. So, that is transients in open channels, and then we can have combined free surface and pressurized transient flow, and that is the third kinds of system. So, we can classify the hydraulic transients with respect to what kind of system we are dealing. We can have hydraulic transient closed systems, we can have hydraulic transients in open system, or we can have hydraulic transients in combined pre-surface and pressurized transient flow system. So, here in this lecture we are only discussing the transients in closed conduits, and then also with respect to how whether the fluid mass is whether it is distributed as in the case of a pipe flow, or it is whether it is lumped as in the case of surge tank. We can also classify the hydraulic transients into distributed system and the lumped system. So, these are some of the classifications with respect to the hydraulic transient. Now here we will discuss the hydraulic transients in closed conduits or pipes system. So, and also we will say we can see that the pipe system which we discuss is in the distributed system, and also we will discuss briefly we will discuss the hydraulic transients in with respect to lumped systems as in the case of a surge tank. So, as far as distributed system is considered, we will derive the basic equations, the fundamental equation, by assuming a fluid is compressible and then transient phenomenon occurs in the form of traveling waves. So, example is water supply pipes, when due to sudden closure of a valve we get the hydraulic transients. So, that is the case of distributed systems. And then as far as lumped system is considered, it is a change in flow condition instantaneously throughout the fluid. So, there is a sudden mass of fluid, with respect to that change what happens. So, that is the example is oscillations in surge tanks. So, now with respect to these fundamentals which we have discussed so far on the hydraulic transients, we will derive the fundamental governing equations with respect to the hydraulic transients. So, the governing equations are the dynamic equations and the continuity equations. So, mathematically these transients in a distributed system like in the pipe flow or the closed conduits are represented by partial differential equations, and as far as lumped system, transients in lumped system is generally described by ordinary differential equations. So, how to classify whether the system is distributed system or the system is lumped system. So, we can use a simple relationship between this omega L and A, where omega is the frequency of the which the wave travels, the omega is frequency, L is the length of pipe, and A is the wave velocity. So, if you find this relationship omega L by A, if it is less than 1, then the system is lumped system, and if it is greater than or equal to 1, then we call it as a distributed system. So, this classification we can have with respect to the frequency of the wave movement and also the water hammer velocity or the wave velocity and the length of the pipe. So, now we want to we want to see what are the governing equations with respect to the unsteady flow or the hydraulic transients for closed conduits or the pipes, unsteady flowing pipes. So, here we will discuss the equation of unsteady flow through closed conduits. So, as we have seen earlier, here also we use some fundamental assumptions to make the system simpler and then to derive the governing equations. So, here since we are dealing with the closed conduits or pipe as far as unsteady flow is considered, so we assume that flow is one dimensional and velocity distribution is uniform over the cross section of the conduit. So, the flow is which we are considering here, the pipe flow we consider as one dimensional flow, and then also we consider that the cross section, the velocity distribution is uniform over the cross section of the conduit. And second assumption is conduit walls and fluid are linearly elastic. This is second assumption. And third assumption is formulae for computing the steady state frictional losses in conduits are valid for transient state also. And so, based upon these three assumptions, here we derive the unsteady flow equations which are described by the dynamic and the continuity equations. So, to see this to derive this dynamic equation and continuity equation, we consider here say there is the flow through pipe here or the closed conduit, and flow is going this direction. So, here the radius of the pipe is r, and the datum is here is the datum, and here the total head is the piezometric head is here h, and here it is plotted, the instantaneous hydraulic gradient line is plotted for this system. And here say we consider two sections at section section 1 here at a distance x from the origin. So, it is the discharge is q and the head is h, and then at section 2 here at a distance delta x. So, x plus delta x, the discharge is changing to q plus del q by del x into delta x, and h is changed to h plus del h by del x into delta x. So, here the head is h plus del h by del x into delta x. So, this is the control volume which we consider here, where this x is the distance, q is the discharge, v is the flow velocity, and h is the piezometric head. So, we consider the control volume between section 1 and 2 to derive this dynamic equation. So, now if you consider the free body diagram of the fluid element, we can see that. So, here we consider a system between section 1 and 2. So, if we consider the fluid element between section 1 and 2, we can see that here the forces acting are the force on this direction with respect to the pressure force F1, and here on this direction here F2, and here there is a shear force S, and then the weight of the fluid elements. Here we assume that the pipe is horizontal. So, we do not consider in the derivation the weight of the fluid element. So, F1 we can, with respect to F1 we can write here for this system, F1 can be written as F1 is equal to gamma A into H minus Z as in equation number 1, and F2 we can write gamma A into H minus Z plus del H by del X into delta X as in equation number 2. So, now as far as shear force is considered, we can use the Darcy's-Weisbach formula. So, from which we have seen earlier, we can write the shear force AC is equal to gamma by G into F V square by 8 into pi D into delta X, where D is the diameter of the pipe and then G is the acceleration due to gravity, gamma is the specific weight, F is the friction factor and V is the average velocity across the section as in equation number 3. So, the resultant force we can, for this system we can write F is equal to F1 minus F2 minus S in equation number 4. So, from equations 1, 2, 3 and 4 we can write F is equal to minus gamma A del H by del X into delta X minus gamma G into F E square by 8 into pi D into delta X. So, for the given system here, so we considered here this section 192. So, this is F1 F2 S. So, here F is equal to F1 is this direction, this is F2. So, F2 minus S. So, we finally we got the resultant force F is equal to minus gamma A del H by del X into delta X minus gamma by G into F E square by 8 into pi D into delta X as given in equation number 5. So, here if we use Newton's law of motion, we can write force is equal to mass into acceleration. So, mass of the element with respect to the fluid between section 1 and 2, we can write the mass of the element is equal to gamma by G into A into delta X. So, we consider the between section 1 and 2 the distance is delta X. So, gamma by G into A into delta X, and then acceleration is considered, we can write acceleration of the element is equal to dV by dt. So, that this we can write as with respect to this the acceleration is dV by dt. So, now if we use equation number 5 and 7, this relationship for acceleration, this is mass and acceleration together. So, we can write, and if you divide by gamma A into delta X, we have dV by dt is equal to minus G into del H by del X minus F V square by 2D as in equation number 8. So, now from calculus we can write this dV by dt, which is the acceleration is equal to del V by del T plus del V by del X into dx by dt, which we can, since dx by dt is equal to the velocity v. So, that we can write dV by dt is equal to del V by del T plus v into del V by del X as in equation number 9b. So, that finally we can write the dynamic equation as del V by del T plus v into del V by del X plus g into del H by del X plus f v square by 2d is equal to 0 as in equation number 10. So, here you can see that in most of the transient problems, this v into del V by del X is much smaller than the acceleration del V by del T, local acceleration del V by del T. Therefore, we can neglect this term. If we neglect this term and if we account for the reverse flow v square, we can represent by writing modulus v into v. So, that and then transforming q is equal to a into v. So, finally, this equation number 10 we can write as in del q by del T plus g into a into del H by del X plus f by 2d a into q modulus q into q, that is equal to 0 as in equation number 11. So, this is the dynamic equation with respect to the unsteady flow or the transient flow in the or through the closed conduits or the pipelines. So, finally, we got the relationship in terms of discharge. So, here this V is put in terms of Q by A. So, finally, we got the relationship in terms of discharge as in equation number 11. So, this is the dynamic equation which we have derived based upon the Newton's second law. So, now the second equation for the unsteady flow through closed conduits or pipes we can obtain from the continuity equation. So, to derive the continuity equation, let us consider a system like this. So, here you can see, here we consider a control volume, say the flow is taking place with respect to pipe which we consider. So, this is the control volume. So, inflow is here and outflow here, and the radius of the pipe is r, and with respect to the change, let us assume at section 2 in this radius is changed r plus dr. So, now the volume of fluid inflow at this location V under bar V in is and outflow V under bar out can be given as V under bar in is equal to the velocity small v into pi r square into delta t as in equation number 12, and V out V bar out is equal to V plus del V by del x into delta x into pi r square into delta t as in equation number 13. So, with respect to inflow and outflow, the change in volume is delta V in is equal to delta V in minus V out, that means the change in volume is equal to minus del V by del x into pi r square into delta x into delta t as in equation number 14. And then the pressure change delta P during delta t, the time we can change in time, we can write as del P by del t into delta t. So, this delta P causes the conduit walls to expand or contract radially, therefore, the fluid element to decrease or increase due to the compressibility effect. So, finally, we can see that the radial or hoop stress for the pipe or the closed conduit which we consider, we can write sigma is equal to P into R by E, where P is the pressure and R is the radius of the pipe and E is the wall thickness. So, that we can write sigma is equal to P R by E as in equation number 15, and then the change in hoop stress we can write delta sigma is equal to del P into R by E. So, that is equal to del P by del T into delta T into R by E as in equation number 16. So, the change in strain we can write. So, the strain change will be delta epsilon, that is equal to delta R by R as in equation number 17, and if the conduit walls are assumed linearly elastic. So, that Young's modulus we can write as E is equal to del sigma by del epsilon, that means change in stress by change in strain. So, E is obtained from this equation number 16, 17 and 18 as E is equal to del P by del T into delta T into R by E divided by del R by R as in equation number 19. So, now we can write delta R is equal to del P by del T into R square by E into capital E, which is the Young's modulus, into delta T as in equation number 20. So, the change in volume delta V R, V under bar R is equal to 2 pi R into delta x into delta R as in equation number 21. So, now using 20, that means this equation 20 and 21, we get delta V R is equal to 2 pi into del P by del T into R cube by E into E, small e into E into delta T delta x as in equation number 22. So, change in volume due to the compressibility we can write V under bar is equal to pi r square into delta x as in equation number 23, and the bulk modulus of elasticity of fluid is K is equal to minus del P by the change in rate of change of volume. So, that is delta V under bar C divided by delta V bar. So, finally, we can use this equation 23 and 24, we will get this delta V C bar is equal to, from this delta V C bar is equal to minus del P by del T into delta T by K into pi r square delta x as in equation number 25. So, finally, if you assume that the fluid density is constant, and now from the lower conservation of mass, the total rate of change in volume V under bar R is equal to del V under bar in plus del V under bar C as in equation number 26. So, if we use equation number 14, which we have derived here, equation number 14, and then if we use equation number 22 is this equation for del V under bar R, and then and 25 is del V under bar C in equation number 26, and if you divide by pi r square, the cross section area of the pipe, delta x into delta t. Delta x is the length we considered, delta t is the time step. So, we will get minus del v by del x minus 1 by k del p by del t is equal to 2 r by small e into capital E into del p by del t as in equation number 27, or finally we get del v by del x plus 1 by k plus 2 r by 2 e small e into capital E into del p by del t is equal to 0 as in equation number 28. So, if you define here this with respect to the square of the water hammer velocity S square as k by rho into 1 plus k d by E small e into E. So, this is with respect to elastic pipe. So, earlier we have seen a relationship for the rigid pipe, A is equal to square root of k by rho, but for elastic pipe we have to write like this. Equation number 29, we can see this relationship is derived in hydraulic transients by Hanif Chowdhury. So, this S square is equal to k by rho into 1 plus k d by E into E as in equation number 29. So, after putting this, and then if you substitute pressure P is equal to rho into G into H and Q is equal to V into A, we get S square by G A into del Q by del X plus del H by del T is equal to 0. So, this gives the continuity equation. So, here A is the water hammer velocity, capital A is the area cross section of the pipe, Q is the discharge, H is the head and T is the time. So, this is the relationship gives the continuity equation. So, here equation number 30, the 11 is the dynamic equation and equation number 30 is the continuity equation. So, this equation number 11 and 30. So, equation number 11 which we have derived here, this equation number 11, and then equation number 30, this equation, both are the governing equations of unsteady flow in closed conduits. So, here you can see that both equations are partial differential equations, and then there are two independent variables here, x and t, spatial dimension one dimensional x in the x direction x, and then time t, and we have two dependent variables, the discharge q and the head h, and here the other parameters like A, the cross sectional area, and D, the diameter, are characteristics of the system. So, we can solve the unsteady flow in closed conduits or pipelines. We can solve using the dynamic equation and continuity equations which we have derived now. So, now to solve these equations, so you can see that when we are analyzing the unsteady or transients in the pipeline system or the closed conduit systems, we can say the equations, the governing equations which we have derived are partial differential equations like the continuity equation here, equation number 30, or the dynamic equation number 11. So, these are partial differential equations. So, to get a closed form solution or the analytical solution is difficult. So, the dynamic and continuity equations are quasi-linear, hyperbolic. So, no closed form solution is generally possible, but say if you simplify the system and then if you linearize the equations as we discussed earlier. So, the equations which are quasi-linear we can linearize, and then the boundary conditions are simple, the considered system is simple, then we can derive some simplified form of the analytical solutions which are available in literature. So, as far as methods of solutions for the unsteady flow in closed conduits or pipes are considered, we can have simplified analytical solutions or so called closed form solutions for a simple system and linearized system, but generally this may not give accurate results when we deal with the practical problems. So, analytical solution is generally used for the verification of the numerical models or other kinds of models which we generally develop. Otherwise, analytical solutions we cannot use for practical problems. And then second one is generally used methodology is numerical methods. So, numerical methods are considered. So, here we are having the dynamic and continuity equations. So these equations we can approximate using various numerical techniques like finite difference method, finite element method, or finite volume method, or boundary element method, or method of characteristics, like that. So you can see that most of the computational fluid dynamics CFD packages also solve this unsteady flow in closed conduits or pipes using various techniques like finite difference method, finite elements, or finite volume methods. So, but some of the commonly used methodologies are finite difference method, say like implicit or explicit finite difference method. So here, as far as finite difference method is considered, the partial derivatives are replaced by finite differences, and then resultant equations are solved. And then finite element method, we use either a Galerkian or the method of weighted residual, or the other different forms of finite element method. We can variation principles like different finite element methods we can use. So actually this is an integral form with respect to we will approximate the governing equation with respect to say an interpolation function, and then we will integrate with respect to the system, and then we will find out the weighted residual, and then we will approximate. So that is basic principles behind the finite element method. So in finite difference method, we may say discretize the domain into grids with respect to one dimensional x direction, and then time with respect to delta t and delta x. So finite element method is considered, we use one dimensional elements, it can be linear or quadratic or cubic depending upon the case, and then generally we may use the time is considered, we may use the finite difference scheme for time discretization generally. So that is finite element method. And another commonly used method is called a method of characteristics. So here the partial differential equations are converted into ordinary differential equations and then solved. So by using this either finite difference method or finite element method, or say other methods like boundary element method, finite volume method, or method of characteristics, there are a number of software packages available for the unsteady flow through pipes or closed conduits, so which we can directly utilize, or based upon the fundamental equations which we discussed, the dynamic equation and the continuity equations, we can develop a computer code by using one of the methodology, and then we can have a computer program to get a solution for the case which we consider, for the problem which we consider. So different methods of solutions are available for unsteady flow problems through the closed conduits. So this is as far as unsteady flow through pipes or closed conduits by considering the distributed systems. And then we have also seen the another system is the lumped system, where we use say as in the case of a surge tank, instead of the distributed system, here we have got a lumped system where a large mass is say either transferred from to the surge tank or going from the surge tank. So here to deal with the here we will briefly discuss the surge tank, which we have discussed earlier. So surge tanks we use to deal with the hydraulic transients or water hammer. So as we discussed, say here if there is a reservoir and then there is a tunnel and then there is a penstock and here there is a turbine. So and from the after water passes through the turbine, it goes to the tail race here. So due to a sudden closure of the turbine, you can see that hydraulic transients or water hammer is generated, and then so to avoid any kind of say fracture in the penstock or the tunnel, to take care of the water hammer, we generally provide a surge tank like this. So this is a simple kind of surge tank. So here you can see that the surge tank is an open standpipe or a shaft connected to the conduits of a system like piping. So here typical surge tank is shown here. So some of the functions of the surge tanks include it reduce the amplitude of pressure fluctuations by reflecting the incoming pressure waves. So whatever incoming pressure waves it reflects in the incoming pressure waves, so that the amplitude of the pressure fluctuations are reduced, and the surge tank improves the regulating characteristics of a hydraulic turbine. So since here we have a large standpipe or so called surge tank or shaft, here you can see that we can easily control what is with respect to the turbine here by using valves. So it improves the regulating characteristics of the hydraulic turbine, and also it acts as a storage for excess water during load rejection, and it is also referred as surge shaft or sometimes surge chamber, depending upon the say which way we deal. So, there are different types of surge tanks. A simple surge tank is shown here. This is a simple surge tank connected with the closed conduit or pipe system, and this is called an orifice tank. So, here there is an orifice arrangement here, and this is called orifice tank, and then there can be differential tank, like you can see the water is at different levels with respect to this system. Say this is a riser. So, this is one orifice arrangement, and also we can have a one way tank like this with respect to check valve. It is only flow is allowed this direction. So, there can be a one way tank also. So, there can be different kinds of surge tanks, different shapes of surge tank. So, that depending upon which type of problem we want to deal with, we can use. So, also here you can see a closed tank with a air shaft or throttling valve. So, that with respect to we can keep pressure here, it is called a closed tank, and then we can also have tank with galleries. So, here you can see lower gallery, upper gallery like this. So, all these details you can see in the textbook by Hanif Chowdhury, Applied Hydraulic Transients. So, now we will just briefly discuss what are the Gaminian equations for such a system of the lumped systems. So, here also we use some of the assumptions like the conduit walls are rigid and liquid is incompressible, and inertia of liquid in surge tank is small compared to that of the tunnel. Hence, we can neglect the inertia of the liquid in surge tank, and then also the head losses in the system during transient state can be computed by using the steady state formula. So, as we have seen the case of unsteady flow through pipes or closed conduits, which we have derived earlier. So, very similar way we use some of the assumptions here. So, then we consider a system, a reservoir, and then here we have got a pipeline, and then there is a surge shaft or surge tank, a simple surge tank, and then here we have a valve, and that goes to turbine. So, if we consider a simple system like this, so here we can see, so to derive the dynamic equation we consider a control volume like here. So, that here if we consider control volume, so the forces acting, so the pressure between section 1 and 2, here if this is section 1, here section 2. So, here the force on section 1 is given as F1 is equal to gamma AT is the cross section of the tunnel. So, gamma AT into H0 minus HV minus HI. So, this here this H0 is the initial head, and then HF is the head loss due to friction, and HV is the, if we consider the energy gradient line, also HV is the energy loss or the velocity head loss, and then if with respect to initial loss HI. So, now F1 is obtained as gamma AT into H0 minus HV into HI, and then F2 this side is considered, we can write with respect to this figure gamma AT into H0 plus Z. So, and then F3, that means with respect to the friction loss, here we can write F3 is equal to gamma into AT into HF, which is the friction head HF. So, now the resultant force will be sigma F is equal to, with respect to these three equations we can write sigma F is equal to gamma into AT into minus Z minus HB minus HI minus HF. So, here now if you using Newton's second law of motion, we can equate this net force, resultant force to the mass into acceleration. So, here if you consider this mass as gamma L by G and acceleration we consider as mass is gamma L into G by G into A, and then we write with respect to acceleration dV by dt. So, that is represented by dq t by dt. So, that way we can write gamma L by G into dq t by dt, where dq t is the discharge through the tunnel. So, that is equal to this gamma AT, the net resultant force gamma AT into minus Z minus HP minus HI minus HF. So, where here H is equal to HP plus HI plus HF. So, that we can write this is equal to, with respect to Darcy's equation which we have seen earlier, Darcy's back equation we can write C into QT into Qt. So that here this relationship finally we can write as dQt by dt is equal to G into AT by L into minus Z minus C Qt into modulus Qt to take care of the direction of flow, where C is a coefficient. So here Qt is the discharge through the tunnel, AT is the cross section area of the tunnel, L is the length we consider from here to here, and then C is the coefficient, and Z is the datum, the head difference here with respect to this. If this is the datum here, this Z is represented here. So now all the parameters are defined here. So we get this as the relationship for the dynamic equation with respect to the surge tank here, and then the continuity equation we can simply write the total discharge through the tunnel Qt is equal to Q what is going to the surge shaft Qs plus what is going to the turbine Q turbine. So Qs is the flow into surge tank, Q turbine is the turbine flow. So writing Qs as As into, with respect to this Qs what is the surge tank, Qs as As into area cross section of the surge tank is As. So As into dz by dt. So the above this equation becomes dz by dt is equal to 1 by As into Qt minus Q turbine, the discharge in turbine. So here Qt is the tunnel discharge, Q turbine is the discharge through the turbine, Z is defined here, this head difference, and As is the area cross section of the surge tank, and T is the time. So this gives the continuity equation, and a dynamic equation is obtained by here this relationship. So here this dynamic equation, continuity equations are valid for the tail rise in the surge tank. Here you can see that both equations are ordinary differential equations. So we can get some closed form solutions for this also, since these are ordinary differential equations. But generally here also we use numerical methods like finite difference method and Runge-Kutta method we can utilize to get solution for a surge tank. So to finally to summarize, so in this section of pipe flow systems we have seen the basic principles of pipe flow, the Gamiani equations, Darcy-Swisbach equation. Then we considered the laminar and turbine flow systems, and we have seen the losses in pipe flow, and also we have discussed the multiple pipe flow systems like pipe in series, pipe in parallel, branching pipes, etc. we have discussed, and also we have seen the pipe networks and solutions we have seen with respect to the pipe flow system which we discuss here. And finally in this chapter we have discussed the unsteady flow in pipes, the hydraulic transients and the surge tanks. So this is the last lecture of this fluid mechanics course. So here we have seen the various aspects of fluid mechanics, and also we have seen some of the advanced topics on fluid mechanics, including the boundary layer theory and the unsteady flows, and also we have seen various fundamentals and also some of the applications as far as fluid mechanics course is considered. So in this 42 lectures we have covered most important aspects of the fluid mechanics, but still say fluid mechanics is a very large subject where say different large other aspects are also there, like we have not covered the compressible flow or we have not gone through the details of computational fluid dynamics. So other number of topics are there, but the main purpose of this course was to go through the fundamentals and some of the advanced topics which are generally used for bachelor level as well as master's level courses in IIT Bombay. So finally, to conclude this video course, so here the acknowledgements. So I am very thankful to Professor S.G. Joshi, who has reviewed this video course with a critical review of the course videos as well as slides. So I am very thankful to Professor Joshi for the critical review given on the videos as well as slides. And I am also very much thankful to my students, Mr. Suman K, Mr. Samuel, Mr. Narendra, who prepared most of the slides. Very beautiful slides were prepared by the students, so I am very thankful to them. And also I am very thankful to the CDEEP staff who has done a wonderful job to in this videoing of this course, and with say very good quality and all this video recording. I am very thankful to them. Finally, I am thankful to my family, my wife Dr. Manjush, and my kids, IPAN based, since I put a lot of efforts to develop this course to this form. So I am also thankful to them. So finally, I hope all these 42 lectures which has been given in this fluid mechanics course will be useful to the teachers as well as students, bachelor level as well as master's level, who is taking fluid mechanics course. Thank you very much. So I hope you will enjoy these lectures.